Number 1, version 2, just to be secure. Okay, which of the following molecules contains a central atom with sp3 hybridization? All right, I'm just going to put the A, B, C, D, and E in here and talk over the document. If we're looking for sp2 hybridization, what type of geometry, electronic geometry can we expect? We have 3 sp2 hybrid orbitals, right? So they are going to be arranged in such a fashion that you can spread them out into 3 positions, which means trigonal planar. That's the only way that you can get 3 arranged like that. And then with something in the center, whatever that happens to be, bonded like that, the bond angles are going to be 120 degrees. So let's look at what we've got here and see which ones give us 3 groups around a central atom. The first one, we have 2 possible central atoms, aluminum and phosphorus, but they each have 4 groups around them. Right? So they're going to be tetrahedral. So these guys are both tetrahedral. B, we do have 3 groups around that boron. So this is a good, that would be a good selection. C has 3 bonding pairs and 1 lone pair, which makes 4 groups, and that's also tetrahedral. D has 1, 2, 3, and notice that it's got a lone pair stuck in there on each one of those nitrogens. That's another 4 groups. So you're tetrahedral again. And then the bottom one, you've only got 2 groups around that beryllium. This is going to be deficient in the octet deficient, right? Very deficient. But only 2 groups means linear, right? So this is the only one, the sp2 trigonal planar. That's the only one that satisfies the conditions. But when I answer a question like that, I've got that table right here in my mind's eye saying what are the relationships of the various hybrid orbitals and to the VSEPR model. Okay, number 3. Consider the molecule of the following hybridization choices. I better write this one on the board. So we've got 4 carbons with single bonds between them. And then we've got a triple bonded nitrogen. And let's see, on this second carbon, we've got a chlorine and a hydrogen. And this number 2 has double bonded oxygen, and then these are each hydrogens. There's your molecule. All right. There's something missing from this diagram. It doesn't show any lone pairs. Right. This one's going to have a lone pair just like that. Just think of this as a cyanide. When we drew the cyanide molecule with the hydrogen out here, that nitrogen's got to have a lone pair. And you can think of it in terms of octet too, right? 2, 4, 6. It's got to have that to make 8. This oxygen, we may not need it, but it's got 2, 4. Now it needs 6, 8. And then this chlorine, it needs an octet also. So there are lone pairs. Now the question is, what's the hybridization of the carbon atom that's double bonded to the oxygen? This one right here. it's got how many groups around it? 1, 2, 3. Its hybridization would be sp2. So you have one S, two P's that give you that trigonal planar geometry. Okay. Well, let's see. Well, why don't we do number 4 also? 4 says, what's the hybridization around the nitrogen atom? Nitrogen's got 2 groups. So its hybridization is going to be sp. All right. And then we get down to 5. And we're looking at, this is more extensive. Actually, it's a different molecule. Okay, never mind. Back to the drawing board. Okay. So for this one, we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. And those numbers under there, they're not like subscripts for these. They're just identifying the carbons. Which number carbon is it? Let's see. These two have a double bond. Then we have 1, 2, 3 singles. And then we have a nitrogen out here. Right? It's got to have that one. This one has 2 hydrogens. This one has an oxygen. This one has 1 hydrogen, and this one has 2 hydrogens. Okay. Now remember, when we write these organic molecules, these hydrogens belong to the carbon here, and this carbon is bounded to that carbon. These hydrogens are not bound to any neighbors because they can only have 1 bond anyway. That's just notation convention. All right, specify the hybridization of each carbon atom. This should be fairly simple. Right? How many do we have around this carbon? We've got 1, 2, 3. Right? So I'm going to write not bonds, groups, numbers of groups. Right? Down this row, we've got 3 around that one. We got 1, 2, 3 around this one. 1, 2, 3 around that one. We've got 1, 2, 3, 4 around this one. We've got 1, 2 around this one. And that's all the carbons. Yeah, okay. So 3 means sp2, 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 sp3, because we have 4, and sp. So sp2 3 times, and then sp3. That would be A. A would be the best answer for that one. All right, number 6. Okay, the hybridization of selenium in selenium hexafluoride. Well, let's see. Selenium is in the oxygen group, so it has 6 valence electrons, and then 6 times 7 for the halogen is 42. So we have 48 electrons. Selenium, 1, 2, 3, 4, 5, 6, right? Two, 4, 6, 8, 10, 12. 36. 4, 6. 6 times 6 is 36. We're going to use them all up. There are no unbonded pairs in this molecule. Okay, so this means VSEPR says with 6, we've got an octahedral arrangement. And we need 6 equivalent, 6, I hate to say equivalent orbitals, because once you get into these trigonal bipyramidal and octahedrals, then you get odd bond angles. They're not as clean as the trigonal planars. Anyway, we need 6 equivalent orbitals. And in order to do that, we've used up 4 of them like that. All right, we need 2 more. So D2sp3 would be octahedral. All right, how about number 9? A pi bond is the result of what? Well, pi bonds have to be off axis. If we have 2 elements here, we can have 1 sigma. That's it. We can have 2 pi's if we have available p orbitals that can overlap. Let's stick to 1. So we won't get really messy. And we can overlap these kind of sideways. And that gives us a pi bond. So we don't overlap 2 s orbitals. We don't overlap an s and a p. I'm running down the list, A through E. Overlap 2 p orbitals along their axis. Not along their axis. This is their axis, so we can't do it along their axis. It's off axis. It's a sideways overlap of 2 parallel p orbitals. That's D is the best answer. Okay. Number 10. Okay, here we got some organic convention again. If we've got these 3 molecules, okay, and their formulas are given. C6H6 is the first one. Then C6H8. Yep, and C6H10. C6H10. All right, we've got this ring structure to go by. And whenever an organic molecule is drawn like that, each one of these intersections is a carbon atom. Okay, so we've got a 6-membered ring for each one of them. All right, and we're shown a double, double, double here. Okay, anywhere you have a carbon atom, it's either got a bond to it. There's either 4 bonds, 3 bonds and a lone pair, 2 bonds and 2 lone pairs, or if it's got a double bond, then you've got 1, 2, 3, 2, 4, 6 electrons to that carbon, and you need another pair. So the other pair that we don't write is the hydrogens. So each one of these carbon has a hydrogen sticking off of it. Like that. That gives this carbon 4 bonds, 2, 4, 6, 8 octet. Okay. So these guys are sigma bonds, and these are pi bonds. So that's an oversimplification because we know that each one of these bonds is equivalent. So we don't have a double bond here and a single bond there. It's really it's delocalized. I think we showed you a picture of one of those. It's like a donut around the top and bottom. But for answering this question, that works just fine. The other one, now this one does have a double here and a, well, actually, what we get is this resonance around the whole molecule. Here we only get resonance like that. And here we get no resonance. That double bond is all by itself. And we would have hydrogen here, 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 and here. Then we'd have 2 here and 2 there. That makes 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Around this one, we'd have 1 there, 1 there. And we'd have 2 around each one of these. Right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there we have all our hydrogens accounted for if I label them correctly. Okay, what's the question? Which molecules have p orbitals that share an electron pair to create pi bonding? Which molecule? All of them. To answer that question, they all have it. All right, so A is all, which would be D. But we've also got number 11 that uses the same setup. So let's see what that question is. Which molecules have equivalent carbon-carbon bonds throughout the molecule? Okay, I blew by that one pretty quick, but this is the only one. Wait a minute. Throughout the molecule, this is the only one that has equivalent bonds all the way throughout the molecule, because we've got resonance for the entire ring structure. We've only got resonance here for part of it. So this would be Roman numeral 1, right? This one right here. Okay. That's why these guys, these aromatics, this is an aromatic compound, benzene. Anything that's aromatic is extremely stable. All right, number 12. The electron configuration of a particular diatomic species is, and this is the molecular orbital shorthand notation. What's the bond order of this species? All right, I'm going to work from that picture so I don't have to redraw the electronic structure. But when we do the bond order, we calculate everything's divided by 2. We want the number of bonding electrons minus the number of anti-bonding. Okay. So the number of bondings, we just look for the ones that don't have stars next to them. So let's see. The first one we got 2 sigma 2s, and we've got 2 on the sigma 2p. That's 4. And then we've got 4 more on the pi 2p, so that's 8. So we have 8 bonding. How about anti-bonding? Look for the stars. We've got 2 on the sigma 2s star and the pi 2p star. So we have 2 plus 2 is 4 divided by 2. So that's a bond order of 2. Okay.
The anti-bonding ones are the ones that have the stars.
Yes. Mm-hmm. Correct. All right. 13. As the bond order of a bond increases, the bond energy does what? Think about when we say bond energy, how much energy do we have to put into the system? Positive value to break the bond. So the bond energy, as the bond order increases, the bond energy increases. And how about the bond length? The bond length usually goes the other direction. As the bond order increases, the bond length shrinks, because think of it as it's got a stronger spring in there and it's pulling those atoms together. So the bond length decreases. So increases, decreases is the correct answer. That's C. All right, how about 15? How many unpaired electrons in the F2 2+ ion are based on molecular orbital theory? And it gives you the order of the molecular orbitals, so you don't have to figure them out. All right, so I will write these in. Okay, so this is F2 2+. F2 2+. All right. hold that thought. We're going to put these sigma 2s, and sigma star 2s. Yep. S. And then we have sigma from the p's, sigma 2p's, and then pi 2p, correct? And then pi star from the 2p's, and sigma star from the 2p's. Okay, remember, these sigmas only have one orbital each. The pi's have two. So those are places where you can put electrons. Now we need, how many electrons are we working with? Well, we've got, notice that we left out the 1s's. So we're really we're dealing with valence electrons. We only count up the valence electrons here because we left out the 1s's. Okay. All right. So the valence would be 7 for each fluorine, 7 times 2, but we're down by 2. That gives us a 2 plus. So it's minus 2. So it's 14 minus 2 equals 12 electrons. So we have to position 12 electrons. And the Aufbau principle says we're going to put 2, 4, 6, 7, 8, 9, 10, 11, 12. All right, with Hund's rule, we have to split them before we compare them. All right, now back to the question. How many unpaired electrons in this? We have 2 unpaired electrons. Okay. In order to answer that question, we have to go through that whole rigmarole. Oh, by the way, is there sp mixing in this molecule? I don't think so. Because the sigma 2p and the pi 2p are in sigma pi order. That's no mixing. And that stands to reason, right? Because our dividing line is between nitrogen and oxygen. So the fluorine should have no mixing. If we had mixing, say if we were in the nitrogen range, then that sigma 2p and the pi 2p would be flipped, and the pi would come first. All right. 19. 19. The hybridization of the central atom in ClF2 plus. Oh, okay. So we're backing up. We put the vehicle in reverse. ClF2 with a plus charge, right? Okay. So we've got 1, 2, 3 halogens. 3 times 7 is 21, but we're deficient by 1. So we really only have 20 electrons. Chlorine, the clue here is that chlorine is probably in the middle. So we'll put chlorine in the middle. Excuse me. And then we'll put a fluorine here and a fluorine here, which is minus 4. That's 16. 2, 4, 6, 8, 10, 12. That gives us octets for those two. It's minus 12 is 4. And if we put here, here, and here, here, now chlorine has an octet. So hybridization around the central atom. So it's got 4 groups. This hybridization is sp3. All right. Scoot down to 21. All right. Which of the following does not contain at least one pi bond? A, B, C, D, and E. So we've got H2CO, CO2, C2H4, C2H6, and none. At least one pi bond. Well, we've done carbon dioxide ad nauseum. We know what it looks like. And it's got two pi bonds. You got one pi bond here and one pi bond there. Let's see. We can do the rest. Right, so this one's going to have carbon 4. 2 times 4 is 8, plus 6 is 14 electrons. Let's count the electrons first. So this one's going to be 8 plus 4 is 12 electrons. This is going to be 4 plus 6 is 10, plus 2 is 12 electrons. Okay, so this one's going to have a carbon in the middle, oxygen, and 2 hydrogens. So that's 2, 4, 6. We have 6 more. 2, 4, 6. Okay, we've got to make an octet here, so we're going to take those two, make a pi bond. Okay, so which one does not contain a pi bond? Well, that contains a pi bond. This one contains a pi bond. How about this one? We got 2 carbons and 4 hydrogens. 2, 4, 6, 8, 10. So we got 2 more. Put them on that one. Well, now we can make an octet. All we have to do is take those 2, make a double bond. Now they each have an octet. So that one has a pi bond. How about this one? 14. So we're starting similar position. Now we have 6 hydrogens. They'd be positioned like this. 2, 4, 6, 8, 10, 12, 14. That's it. This has no pi bonds. All right, let's see. Scoot. 24. Or Lewis structure. Complete the Lewis structure for the following molecule. This molecule has so many sigma and so many pi bonds. Okay. So it's given us the structure. Let's see, 1, 2, 3, 4 carbons and a nitrogen. All right. And then this one has an oxygen. This one has carbon and 3 hydrogens. And this one has a hydrogen. This one has 3 hydrogens. Okay, the question is, do we have all of our electrons accounted for? Well, first thing we need to do is count them up. 1, 2, 3, 4, 5 carbons is 20. Right? 4 times 5 is 20. Then we have 1, 2, 3, 4, 5, 6, 7. 7 hydrogens. Then we have an oxygen, which is 6. Then we have a nitrogen, which is 5. So this should be the total number of electrons. 38, right? Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that's 12 electrons. Working from the outside in, we have, we can put 2, 4, 6 here, and we can put at 6 and 2, 4. Where are we going to put the last 2? Well, I wouldn't put them here simply because it wouldn't balance, right? If you had 2 here, then you'd only need one of those there, and then this one would be deficient. So I would put the 2 over here. All right, so let's see. We need 38 total, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. I didn't count right. Let's try it again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. There we go. So all of our electrons are positioned. Now, this was probably the one that would give you the most trouble. Where do I put that last pair? This one we can move and make our octet there. That means this one, you can't make another octet on. You put a double bond on that side because it will exceed the octet. So we put this one over here. Like that. No, we don't want to do that because it's already got. And you didn't stop me. That pair here needs to go there. Because we still have to make an octet for oxygen. That's another reason for putting that last pair here, so that we could do it. Actually, you know what? That was the wrong place. That last pair doesn't need to go on that carbon because we're working from the outside in. It needs to go here. That last pair needs to go right there. That way, now it's a simple move from here to there. Okay, so far? All right. How many sigma bonds do we have? You just count up all the spaces between elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 sigmas. And how many pi bonds? 1, 2, 3. Okay. 13 and 3. Okay. Let's see. 26. Okay. Yeah, 26. Once I get to 26, we're halfway. And we got plenty of time. I'm probably going to go past half. Consider this skeletal structure. What are we going to consider about it? Draw the little structure. How many pi bonds does the molecule contain? Well, we have to assume that that's it. That's all there is. Right? There are no hydrogens in there. So this is 5, 10, and 8 is 18. 18 electrons. 2, 4, 6, 8, 10, 12. 6 more? Is that right? Let's see. Nitrogen is 5, right? 5 and 10. And 4 is 8. Yeah, that's right. 18. Oh, excuse me. I didn't count these. 2, 4, 6. That gets rid of those. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, they're all accounted for. Now we got to make, since we're working from the outside in, that's where those electrons go. And we're going to make an octet. So if we put this one here, that's an octet. Put those two there, now we have an octet. So that would be the Lewis structure. And how many pi bonds does the molecule contain? 1, 2, 3, 4. 4 pi bonds. Okay. 27. Which Which of the following molecules contains the shortest carbon-carbon bond? All right. A, B, C, D, and E. I'm gonna put these up here. C2H2, C2H4, C2H6, and C2Cl4. C2Cl4. And this one says B and D must have the same shortest carbon bond. All right. So if we draw this one out, that's 2 times 4 is 8 plus 2 is 10 electrons. This would have 2 more electrons, be 12. 2 more than that, it'd be 14. This would be 4 times 7 is 28. And 8 is 36, right? Okay. So we've got a carbon and then a hydrogen on either side. And that keeps 2, 4, 6. So we need 4 more. There we go. Now to make an octet, can't go this way, so we have to go in. One's here, one's there. That happens to be acetylene. Or other parts of the world, they call it ethine. So I like acetylene better. Okay, we got 2 here, right? Then we got these. We drew this one earlier. There, that takes care of that one. We also drew this one earlier. It's 18, 14, yeah. And this one is carbon, carbon, chlorine, chlorine. So that's 2, 4, 6. That means 30 left over. 2, 4, 6, 8, 10, 12, which would be 18. That's going to be right. Oh, 4. I'm sorry. We need another chlorine down here, chlorine down here. 6, 2, 6. That's 8, and 8 is 16. Right? So that's 2 electrons left. We'll put them right here. So these guys already have octets. We're just going to move this one into the middle. Do that. So this one is similar to that one, only instead of hydrogens, it has chlorines. Okay. Which one has the shortest carbon-carbon bond? Well, the first thing you would do is look for single, double, triple. Right. That's single, that's going to be the longest bond. This will be the next longest bond. Excuse me. This will be the next shortest bond. This one could be the same as that one. And I'll explain that in just a minute. But this one is going to be the shortest bond, that triple bond. The difference between this one and this one is these big electron withdrawing groups. Chlorine is more electronegative than hydrogen is. So it's going to draw electron density away from that bond, and that will lengthen the bond. So that's why I say this bond length and strength could be about the same as that one. Even though it's double, it might act like a single or pretty close to it. Simply because these guys are drawing electrons away from that bond and weakening it. But that wasn't the question. The question is, which one's the shortest, and that's it. All right. Let's get a couple more out of this, and that will take the pressure off of next Tuesday. 28. 28. When comparing Be2 and H2, Okay. And H2. What are we going to compare? Be2 is more stable because it contains both bonding and anti-bonding valence electrons. H2 has a higher bond order than Be2. H2 is more stable because it only has, okay, we need the molecular orbital set up here. Be2, let's see, how many electrons are we dealing with? If we're gonna, let's do the whole thing from the valence and core electrons. This one obviously is going to be sigma 1s with 2 electrons. Remember from our previous, it has no anti-bonding. This one is going to start off with sigma 1s, sigma star 1s, and then it drops down into the second group. So this is sigma 2s and sigma star 2s. We actually don't even have to consider mixing because we're not going to get into the p's with this one. There are not enough electrons. Beryllium has, let's see, total of 8 electrons. That's core plus valence. So if we do this, 8, 1, 2, 3, 4, 5, 6, 7, 8. Is that right? That means Be2 has a bond order of 0. Did I do that right? 28. Let me look at my cheat sheet. Okay. So the bond order for this one equals 0. And 4 minus 4 divided by 2. We do not expect to form a diberyllium. But we do have bond order here equals 1. 2 divided by 2 is 1. Okay. All right, now let's see if we can answer the questions. Be2 is more stable because it contains both. It contains an equal number of bonding and anti-bonding, so it's not stable at all. So 1 is false. Let's try this. 1, 2, 3, 4. So this one is false. H2 has a higher bond order than Be2. Yes, it does. 1 versus 0. H2 is more stable because it only contains sigma 1s electrons. It is more stable, but is that the reason? Only contains 1s. Well, yeah, it only contains bonding electrons. Contains no anti-bonding. Okay. As far as it goes, I'll say that's true. H2 is more stable because it is diamagnetic. Stability, diamagnetism versus paramagnetism has nothing to do with stability. It just talks about how does the molecule interact with a magnetic field. So 4, we throw that out on principle. Okay. Has nothing to do with stability. Okay, so it's Roman numeral 2 and 3. All right, let's see. 29. 29. Okay, which of the following species is paramagnetic? Paramagnetic is drawn into a magnetic field. Diamagnetic is repelled by the magnetic field. If it's drawn into a magnetic field, it has at least one unpaired electron. Sometimes more. All right, so A, B, C, and D. What is E? E is none of these, of course. So we've got C2, O2, F2, and Li2. Okay, so carbon is going to have mixing. And if we leave out the core and only go to the valence, we only need to work with valence to determine this. We're going to have a sigma 2s, a sigma star 2s, excuse me, a sigma 2p, a pi, let's see, no, pi comes first because it flips. Pi 2p and sigma 2p, then pi star 2p and sigma star 2p. Now we may not need all those. Oxygen is going to be no sp mixing. So we would write this, and this one would come next. And then this one would come after that. Then we would have the pi star and the sigma star. And then F2 would be like O2. So I'm not going to draw that one, just it has the same arrangement. Lithium, actually, it's not even going to get into these. So we could just draw lithium as 2s, sigma star, 2s, and that's probably going to be enough. Okay, so how many valence electrons are we dealing with here? Carbon would have 8 electrons. Oxygen would have 12. Fluorine would have 14 valence electrons. Lithium would only have 2 electrons. So lithium would be like, would have 2 here and none there. Fluorine, well, let's go back to the top. 8, 2, 4, and 4 is 8. Okay, so we don't need the rest of them. And 12, we would have 2, 2. This would be 2. So that's 6. We have 6 more. We have 4 here. And those are all paired like that. Then we would have 2 here. And we have 4, 5, 6, 7, 8, 9, 10. That's 2 more. There. So this one is paramagnetic. Paired all the way through. This is diamagnetic. How about this one? 14. So we would have 2, 2, 2, 4. 4, 5, 6, 7, 8, 9, 10, and 4 more. Those are all paired. Right. You got 4 here and 4 there. Let's see, I needed to put 2 there. See that? Those are all paired. Okay, so this is diamagnetic. And this one is all paired. This is diamagnetic. Right, the only paramagnetic is oxygen. Okay. 30. How many of the following does the bond order decrease if you add 1 electron to the neutral molecule? All right, let's see. Do we have one up here already? We got carbon already. And we got oxygen and we got fluorine. Wait a minute. We need boron, carbon. Carbon and fluorine are there. So we're going to keep these 2. And we need boron and phosphorus. So let's erase this one and erase this one. Well, that's going to mess things up because now I don't have it. All right. All right, so this is going to be sigma 2s. This is going to be sigma star 2s. This is going to be sigma 2p, This would be pi 2p. This is going to be sigma star. No, pi star, excuse me. Pi star. There we go. Okay, now we need to add in, let's see, this carbon is, oh, okay, so they're not like that. Those are just things we work from. So we got carbon and fluorine. Now we need boron and phosphorus. So boron and phosphorus. Okay, boron has 6 total valence electrons. And boron is going to be mixing. So that takes care, I'm going to put them in here so see how far we have to go. 2s, that's 2 in there. Need 2 more. So mixing is going to be pi, no. Sigma, yeah, pi. Pi 2p. And that's 2 more. Okay, and phosphorus. Well, phosphorus is in the 3rd level. So in order to go phosphorus and count the valence electrons, it would be 10, right? Because we're in the 3rd period. But instead of 2s and 2p, we're going to have sigma 3s and sigma star 3s. And phosphorus is going to be mixing. So that means we need pi 3p and sigma 3p. Let's see if that's enough. 2, 4, 8, and then 2 more. Okay, so that would be phosphorus. Now, the question was bond order. How many of the following does the bond order decrease if you add 1 electron? Okay, so this one's full, so we're going to have to add another one out here, which would be pi star with it. 3p. And this one's full, so we got to add another one out here, which would be sigma star. 2p. That was not full yet. That one's full, so we need sigma 2p, right? Because we're going to add 1 electron. That means we're going to have negative charge on each one of these. And where does the electron go? Here it goes there. Here it goes here. 3. Here it goes there. And here it goes there. Okay. So when do we decrease the bond order? 2 ways. If we're adding electrons, then the electron would be added to an anti-bonding orbital. That would decrease the bond order. If we're subtracting electrons, then we subtract it from a bonding orbital. But that's not what we did here. We added 1. So any ones where we added to an anti-bonding, that's it. So difluorine and diphosphorus would give us 2 of these would decrease their bond order. Okay, we don't even have to calculate the bond order. We just have to know where is the electron going in. All right. Okay. Let's see. Do we want to mess with 32? We got time. If I do 32, then yeah. Yeah, let's try 32. I got to get out of here no later than regular quitting time today. So if I can leave a little early, that's even better. So I think we do 32, we'll be way ahead for next Tuesday. Order the following from the shortest to the longest bond. So I got a little note in there. Don't forget the effect of atomic radius and orbital size. So we've got C2, B2, H2, and N2. C2, B2, H2, and N2. So, first place I'd start is what's the bond order? So we have carbon with 4, 8 valence electrons. So let's do that first. Boron has 6, hydrogen has 2, nitrogen has 10 valence electrons. So if we start with the valence molecular orbitals, this is going to be sigma 2s, sigma star 2s, carbon. It's going to be pi, no. Yeah, because we're in the valence. So 2 S's, then P's. So we have pi from a 2p and a sigma from a 2p. And then we go to, let's see, is that 8, 2, 4? That's plenty. So we have 2 here, and 4 there. That's 8. Okay. Boron would be also mixing, but I don't think we have enough. Yes. Pi, 2p. So that's 2, 4, and 2 there. Takes care of that. Hydrogen is obvious. It's 1s2. Nitrogen, all right, we're going to have still have mixing. Sigma 2s, sigma, this is star, and star 2s, and pi 2p, sigma 2p, pi star 2p, and sigma star 2p. So we have 10 electrons, 2, 4, 8, and 2. That's all we need. Okay, so there you have. Now we can calculate bond order for each one. Right. 6 minus 2. Let's see. Is that right? Hold on a second. Let me check myself. This is in pi 2p. Yeah, that's right. 4, 2, 4, 8. Okay, so 6 minus 2 divided by 2. Yeah, that's 2. Okay. And then this one is going to be 4 minus 2 over 2, which would be 1, right? And this one's going to be 1. Already done that one hundreds of times. 4, 5, 6, 7, 8 minus 2 over 2. So that's a 3. Okay. We know that order from the shortest to the longest bond. Well, the shortest bond is going to be this one. N2 is the shortest bond. And the next one should be carbon. What we have to decide on here is, since they have the same bond order, we need to look at what's the distance between the nuclei. Boron is a bigger nucleus, right? Because each boron has 5 protons in it. So we're going to have 10 protons here. We're only going to have 2 protons here. So I think, and this is a bigger atom, and what does it do as we go from left to right? It shrinks, right? But that's only in the same period. Hydrogen only has 1 proton. It can get really close. So I think hydrogen is going to have a shorter bond than this one. Even though they're the same bond order, you can get those single protons a lot closer together before you start feeling the repulsive effects. So I think the next one is going to be hydrogen and then orbital. Make sense? We need to go over that again. We had to break a tie between this one and this one because they have the same bond order. But we're interacting with higher level orbitals. Right? So that also will push them apart because you got more electrons to deal with in this molecular bonding structure, and that pushes the nuclei farther apart because you need room for all those orbitals. Plus, you've got a bigger atom here than you do there, and you can get closer with that single bond. So that's why I put hydrogen first and then boron. Okay, is this a good place to stop? Let's see, 34. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 17, 19. Maybe let's do one more. 32. Yeah. Yeah, let's do 34. Yeah. We got time, and I'll still be in good shape. 34. All right. Which of the following has a bond order of 1.5? So A, B, C, D, E. And we've got O2 plus, N2, O2 minus, C2, and then none. So we've got, this is the only neutral one we've got in here. And this would be, how many valence electrons would be 8 electrons. Oxygen would be 6, and 6 plus 1 is 13. Nitrogen is 10. And oxygen minus 2 would be 11. I mean, minus 1. O2 minus 1 would be 11 electrons. Okay. So let's do oxygen first. Sigma 2s, excuse me. Sigma 2s. Sigma star 2s. Oxygen is non-sp mixing. So the next one would be sigma 2p, and then pi 2p, and then pi star 2p. That's probably enough. And then down here we do the same thing. 2s, sigma 2s, sigma 2p, pi 2p, and pi star 2p. Okay, so let's place our, no, let's go ahead and do this one. SP mixing. 2s, star 2s, then pi 2p, sigma 2p, and pi star 2p. And then carbon mixing. 2s. Be the same as this one. Like an 8. That's probably all we're going to need. So 11 electrons. 2, 4, 6, and 5 more. So we put 4 here and 1 there. This is 10. So 2, 4, 8, and then 2 more here. So we don't need this one. And this one is 13. So 2, 4, 6. 4 is 10, and then 3. And then 8, 2, 4, and 4. We don't need this one. Okay. So, which of the following has a bond order of 1.5? I guess we just have to calculate them. 2, 4, 6, 8 minus 3 over 2. So that's 5 divided by 2, which is 2.5, right? Did I do that right? Yeah. No. 2, 4, 6, and 11. Get those right. No mixing. Yeah. Did I count these right? Yeah, 12 minus 1 is 11. Okay. We know this one's 3. Right? We've done that one over and over and over again. This is, did I count 2, 4, 8? See, that's right. And this is 2, 4, 8 minus 5 divided by 2. So that's 1.5. That's probably it right there. And this is 6 minus 2 over 2. So that's 2. See? Yeah, see. That's 1.5. Okay. Let me make myself a note.